Jai Jagannath. So let us continue the same chapter 22, and this is your lecture number 3, and we are discussing the Gauss law and its application. So in the last class we have solved some application oriented problem using Gauss law. So today we will continue the more application. So first application you see, the question is given under electrostatic condition. That is, electrostatic condition means what? Electrostatic means charge is at rest. So charge are not in motion. So in that type of condition, any excess charge, if it is given on a solid conductor, it will reside entirely on the conductor surface. That means, so we have to prove this. We have to prove this. Suppose you see this is a conducting body, okay, and this is a conductor, and here it is we are discussing what? Electrostatic condition. Electrostatic condition means charge are not in motion, they are at rest. So if we will give the excess amount of charge to this body, what will happen? So all the charge will be distributed on the periphery of the conductor. That means all the charge, extra charge given to this body will reside on the surface, not it will penetrate inside the conducting surface. So we have to prove this. We have to prove using which law? Gauss law. So for any type of so when you will apply the Gauss law, we have to assume a imaginary surface, and that imaginary surface is called Gauss surface. So now let us take a Gaussian surface, that is a sphere. Let us take a Gaussian surface sphere, any surface, no problem. So here you see I have taken A. So A is what? It is a Gaussian surface. It is a Gaussian surface. Clear? And we have already know that electric field intensity inside a conductor during electrostatic condition is equal to 0. I have already discussed this. Electric field intensity inside a conductor in the electrostatic condition is 0. Okay. So now you see we will apply the Gauss law. Suppose I will take, this is the Gaussian surface. I just to take a small element here. So here what is Gauss law? So if you apply the Gauss law within this Gaussian surface, so what is the formula? So as per Gauss law, we know the total electric flux, that is phi, from which Gaussian surface A is equal to charge enclosed divided by epsilon naught. But mathematically we know the flux, electric flux is nothing but the surface integral of electric field intensity. On which surface? On the Gaussian surface. Here which is the Gaussian surface? A is the Gaussian surface. Okay. So that implied inside this conductor electric field intensity is 0. So now you put E is equal to 0. So that implied Q enclosure, that is charge enclosed by the Gaussian surface, divided by epsilon naught is equal to surface integral of E dot dA. So what is electric field intensity inside this conductor? It is 0. So 0 into something is equal to 0. So that implied charge enclosed by the Gaussian surface A is equal to 0. That means within the sphere there is no charge. So if I will take another sphere, again the charge enclosed by this Gaussian sphere will be 0. Then where will be that charge? If we will give the extra charge, where it will reside? So it will reside on the surface of the conductor. That means no charge will come inside the conductor. So all the conductor will reside on the surface. So this principle will apply in the coming application. Okay, so we can say, so that implied charge resides on surface. So this is the, so we will solve example 22.5 in the university physics book. So here you see, we have to derive the electric field due to a charged conducting sphere, that is for either hollow, that hollow sphere may be conducting or non-conducting, or solid conducting sphere. So we will find the electric field intensity at any point due to this condition. Now see, suppose this is a sphere. So this sphere may be hollow sphere. Okay, so whose radius is r. So this sphere may be hollow conducting sphere or non-conducting sphere. So just non-conducting sphere means, hollow non-conducting sphere means, imagine it is a football. So this is a non-conducting surface, but it is a hollow sphere. And conducting hollow sphere means, just you take a copper ball. The ball is made of copper, tennis ball. You see, let us say you take a ball that is made up of copper, but it is hollow. So that means copper is conducting and it is a hollow sphere. And non-conducting sphere means football. Or you can take solid conducting sphere. Suppose this is a sphere which is solid, total solid sphere, just like cricket ball. But cricket ball is a non-conducting sphere. So here you take a solid sphere made up of copper. Okay, so here the radius in the both case are r. Then we have to find what is the electric field intensity at any point, that is inside the sphere, on the surface, outside the point. So before this example, I have already told, just before this I told, whatever the charge is given to a conducting sphere, all the charge will reside on the surface. So this is the very important point. So here all the charges given to this sphere will reside on surface, whether it is hollow conducting or hollow non-conducting or solid conducting sphere. All the charge will reside on what? All the charge will reside on the surface of the conductor. So now let us say the total charge given is equal to Q. Okay. So now R is the radius of the sphere. So what we will do? So I am writing R is radius of sphere. Q is total charge given. So now we have to find the electric field intensity. So first we will find what is the electric field intensity at inside point. Electric field intensity at inside point. Okay. So now let us say this is the sphere. So now see, we are discussing this or this, hollow or solid. So in both cases, charge are residing on the surface. So I am removing this. So whether it is hollow or solid or non-conducting hollow sphere, every time charge is residing on the surface. So we have to find, suppose this is a point, you can say this is the point A. Let us say this is the point A. So okay, I am not taking A point, rather I am taking B, because A indicates the area, so I am taking the B point. So B point is which point? Inside the conducting sphere. So we have to find electric field intensity at inside point. So that means we have to find electric field intensity at B point. So what we'll do? So to find the electric field intensity at any point, we will apply the Gauss law. So what we'll do? So to apply the Gauss law, we have to take a Gaussian surface. So according to the symmetry of the charge distribution, I think if I will take a Gaussian sphere, so that will suit to apply the Gauss law. Okay. So now let us say this from the center, this internal point B is at what distance? Small r distance. Okay. So small r is the distance from center to which point? To B point. And B point is which point? Inside point. So we are imagining a Gaussian sphere which is passing through B point. So we will find what is the electric field intensity at B point. Okay. Then we will find what is the flux, total flux coming out from this Gaussian surface. So for that, what we will do? We take a small element on the surface of the Gaussian sphere. So the area vector is always outward. And these are the positive charge. So electric field intensity, let us say this will lie in this direction. So what is the electric field intensity? At B point? So at B point, let us say the electric field intensity is E. So at B point, electric field is equal to E, say. Okay. So E direction I have given outward. And area vector is also outward. Then what is the flux? So electric flux from which surface? From B surface is equal to surface integral of E dot dA, which is nothing but charge enclosed divided by epsilon naught according to Gauss law. So that implied, you see, electric field vector, area vector, both are in same direction, then it is surface integral of E dA cos 0. Cos 0 is 1. That is equal to Q enclosed by the Gaussian surface. You see, this is the Gaussian surface. So within the Gaussian sphere or surface, there is no charge enclosed within this, because all the charge are distributed on the surface. So total charge within this Gaussian sphere is 0. So I can write charge enclosed is equal to 0 divided by epsilon naught. And since it is symmetrical, this surface is symmetrical about the center, so this electric field intensity is constant, that will come outside. So into surface integral of dA, which is equal to 0. So that implied, whatever may be the surface integral, okay, E into what is the surface area of this sphere? The radius is r. So that is 4 pi r square is equal to 0. So that implied electric field intensity inside this type of conductor, hollow conductor, or your solid conducting surface, or conducting hollow sphere. In that case, electric field intensity is equal to 0. It is where? Inside the sphere. Inside the sphere, electric field intensity is equal to 0 for this situation. Now see, here electric field intensity outside to the point. Now you see, all the charges are residing on the surface of the conductor. We have to find electric field intensity at outside point, that is C point. And this C point is at r distance from the center. So radius of the sphere is r. So what we'll do? To find electric field intensity at this C point, we have to take a Gaussian surface. And that Gaussian surface must be a sphere according to the principle of application of the Gauss law. I have already discussed this. So here we will again take a small element. the area vector will lie outward, and since these are the positive charge, electric field intensity is also outward, and both have same angle, that is zero angle. So now we will find what is the flux due to whole Gaussian sphere. So what we'll do, you know, the flux, the electric flux from which surface? From let us say this is C surface. Let us say this is C surface is equal to what? According to the mathematical expression, it is surface integral of E dot dA. Okay. So on which surface? C surface. That is equal to, but this is the mathematical expression of the flux. But according to the Gauss law, it is total charge enclosed by the divided by epsilon naught. So that implied, so here E and dA are in same direction. So I can write it is E dA cos 0 is equal to total charge enclosed by this Gaussian sphere is nothing but the whatever charge is given on this sphere, so that total charge will come within the Gaussian sphere. So the total charge enclosed by this Gaussian sphere is equal to Q divided by, so here it is epsilon naught, Q by epsilon naught. So that implied E is constant because the Gaussian sphere is symmetrical about this O point. So in every point on the surface, electric field intensity is constant. So bring E outside. And what is the surface integral of dA? On which surface? C surface. So it is Q by epsilon naught. That implied E into surface integral of this surface. That is, you will find the total area. So total area is nothing but 4 pi r square. This is surface area of a sphere, which is equal to Q by epsilon naught. So that implied E is equal to Q by 4 pi epsilon naught r square. This is the electric field intensity at which point? Outside. So electric field intensity outside to the sphere is equal to this. And you see, the Q is constant, 4 pi epsilon naught is constant, this R is variable. If the external point lies far away from the center, the electric field intensity decreases. And outside to the point, electric field intensity depends upon distance. How? It is inversely proportional to R square. As R increases, electric field intensity decreases. So this is the electric field intensity outside to the surface. Then case 3. What is case 3? So what is electric field intensity on the surface? What is electric field intensity on the surface? Suppose this is the spherical conductor. I want to find electric field intensity at D point. D is lying on the surface. So here, if this C point will come towards D point on the surface, then at that time small r will be equal to capital R. So for surface point, small r is equal to capital R. So now you put small r is equal to capital R. So what is the electric field intensity on the surface? So that is equal to Q divided by 4 pi epsilon naught. So this small r is replaced by capital R. So this is the electric field intensity on the surface. And you see, inside the spherical conductor, electric field is 0. On the surface, this is the electric field intensity. And the outside, this is the electric field intensity. Okay. So here you see in which point electric field intensity is maximum. So electric field intensity is maximum at which point? On the surface. And inside the spherical conductor, electric field intensity is 0. On the surface, it is maximum. And as we move away from the surface, electric field intensity decreases. So now we can draw a figure. We can draw a graph between electric field versus. So now you see. What is the conclusion? Electric field intensity inside this charged sphere is equal to 0. Electric field intensity on the surface is equal to, we have derived Q by 4 pi epsilon naught r square. So that is a constant because the radius is a constant. Electric field intensity outside to the point is equal to Q by 4 pi epsilon naught r square, or you can say outside point electric field intensity is inversely proportional to square of the distance. So now if you draw the graph, you see this is the charge sphere, this is the center, and from this point to this point we will get what? Internal point. And inside the sphere electric field intensity is 0. So we will draw a graph between electric field intensity versus distance from the center. So since this area within this point to this point, it indicates it is the within the sphere, so electric field intensity within the sphere is equal to 0. So if I draw, let us say, so this line is coinciding in which axis? X-axis, that is represented by small r. So here electric field intensity is 0 because electric field intensity is taken in y direction. So here electric field intensity is 0. And on the surface it is maximum. That is constant, but it is maximum. So on the surface means this point. So here let us say the electric field intensity is maximum. At this point also electric field intensity is maximum. So what is that maximum electric field intensity? Maximum electric field intensity on the surface is equal to Q divided by 4 pi epsilon naught r square. So here also same, Q by 4 pi epsilon naught r square, that is the maximum electric field intensity on the surface. And as we move away from the surface, electric field intensity decreases inversely. So we can say, so this is the electric field decreases by which relation? Is inversely proportional to r square. So here also electric field intensity decreases as we move away from the center, that is here E is inversely proportional to r square. So this is the analysis of the electric field intensity for a charge conducting sphere. And you see, if the charge is positive, if charge is positive, electric field intensity is away from it. We know this is away from it direction. And if charge is negative, electric field is towards the conducting sphere. Now see, we will solve exercise 22.14. So question is a solid metallic sphere. You see, this is a solid metallic sphere. Okay, so only sphere means it is understood that it is a solid sphere. Of course, it is given solid metallic sphere with radius 0.450 meter. So that is their radius. So radius is given 0.450 meter. So this is the radius of the sphere. And the net charge carries by the sphere is 0.250 nanocoulomb. Since it is a solid sphere, the total charge will reside on what? On the surface. I have explained this. So here the total charge given to the sphere is 0.250 nanocoulomb. Nano means 10 to the power minus 19 coulomb. So we have to find electric field intensity at a point 0.1 meter outside the surface of the sphere. So you take a point A which is equal to 0.1 meter at a point 0.1 meter outside the surface. So from the surface this point A is at what distance? 0.1 meter. But from the center if you see the total, this radius is r. So this is the center. So from the center to this point A, what is the distance? So we can say here OA distance, which is generally taken as, let us say, small r, distance of this point from the center is equal to r plus 0.1. What is r? Radius is given 0.450 plus 0.1 that is 0.55 meter. So this point A, outside point, is lying 0.55 meter from the center. What you have to find? Electric field intensity at this point. So first bit, electric field intensity at which point? A point. And we know, just we discussed now, what is the electric field intensity outside to a conductor? What is the formula? Q upon 4 pi epsilon naught distance square. So here 1 by 4 pi epsilon naught is nothing but 9 into 10 to the power 9. And this is positive charge. So positive charge magnitude is 0.25 into 10 to the power minus 9 coulomb divided by r square. So r is nothing but 0.55 square. So if we will calculate, I think it will come 7.438. 7.438. And what is the unit of electric field intensity? Newton per coulomb. And what is the direction? You see, this is the positive charge. So electric field is always away from the positive charge body. So in this A point, the direction of the electric field intensity is away from it. So we may write the electric field intensity is equal to this, away from the center, away from the center. That is radially outward. Radially outward. Next is second bit. What is second bit? You have to find electric field intensity at a point 0.1 meter below the surface. That means suppose this is a point B, which is equal to 0.1 meter below the sphere. So that means B is which point? B is internal point. B is internal point. And we know electric field intensity at inside point or internal point is equal to 0. So this is the answer. So let us discuss the example 22.9. So here what happens? Electric field intensity, we have to find the electric field intensity due to a uniformly charged, insulated, non-conducting sphere using Gauss law. Okay, so using Gauss law, we have to find the electric field intensity. It is due to what? Charged, uniformly charged, insulated, that is non-conducting sphere. Just take an example. Suppose a cricket ball. So cricket ball is a non-conducting solid sphere. Non-conducting solid sphere. We will give a total charge of Q value, and that total charge Q is uniformly distributed. So that means since cricket ball occupies a space and it is a solid sphere, so definitely since it is uniformly charge distributed, so we have to find here volumetric charge density. Volumetric charge density. What is volumetric charge density? If the total charge given to the total volume of the sphere is Q, and what is the volume? So volume is equal to per sphere, what is the volume? 4 by 3 pi into RQ. So this is your volumetric charge density, which is called rho. Rho is called volumetric charge density. So what is the unit of rho? What is the unit of rho? Volumetric charge density. Charge per volume, coulomb per cubic meter. This is the unit of rho. So now what we will find? First we will find case 1. First we will find the electric field intensity inside the non-conducting charged sphere, internal point. So here what we will do? So according to Gauss law, we will apply a Gauss law. So to find electric field intensity at any internal point, let us say A is the internal point. This internal point is at r distance from the center. So what we will do? We will take a Gaussian sphere. To apply the Gauss law, we have to take a Gaussian surface. That Gaussian surface is our sphere of radius r. Okay. So now we have to find what is the flux through this Gaussian surface. So and you know what is the so here you see this small r. So here small r is less than capital R. Okay. So now you find out what is the flux. What is the flux through this Gaussian surface, Gaussian sphere. So flux, electric flux through which surface? Through the Gaussian surface A is equal to surface integral of E dot dA. Over which surface? Over this A surface, which is nothing but Q enclosure divided by epsilon naught. That implied. So I will not explain again. You see, this is the area vector, this is outward. Electric field intensity is also outward. So electric field intensity and area vector angle is 0 degree. So E dot dA is nothing but E dA. So E is constant. Integration of dA is equal to A is equal to total charge enclosed by the epsilon naught. So that implied electric field intensity E into what is the surface area of this Gaussian sphere? 4 pi r square. 4 pi r square, which is equal to Q enclosure by epsilon naught. So what is the charge enclosed by this surface, by this sphere, Gaussian sphere? You know, the rho is the volumetric charge density. Okay, that means charge per unit volume. So here total charge within the Gaussian sphere is equal to charge per unit volume into volume of this Gaussian sphere. What is the volume of this Gaussian sphere? 4 by 3 pi, radius is smaller, 4 by 3 pi r cube divided by epsilon naught. But what is rho? Rho is nothing but Q divided by 4 by 3 pi r cube. Q by 4 by 3 pi r cube is equal to rho into 4 by 3 pi r cube divided by epsilon naught. So 4 by 3 pi cancel. So we will get okay. So that is equal to what? 4 by 3 pi cancel. You will get Q small r cube by epsilon naught capital R cube is equal to this. So E into 4 pi r square is equal to this, but we have to find electric field intensity. So E is equal to Q r cube divided by 4 pi r square into epsilon naught r cube. So that implied Q divided by r square, r cube cancel, only r. So Q into r by 4 pi epsilon naught r cube. So this is the value of electric field intensity at internal point, that is inside the sphere. This is the value of electric field intensity. And you see, the total charge given is constant, r is constant, but small r is variable because we are taking the small a point is arbitrary within the sphere. The small r is variable. So if small r is variable, we can say at internal point electric field intensity is directly proportional to small r. So if from the center to the surface, if small r, that is r, increases, then electric field intensity increases. Then what is electric field intensity at the center? Electric field intensity at the center. At the center, what is the value of small r? 0. So if we are discussing about this point A, so which is r distance. Now if that point will coincide with the center, small r is equal to 0. If small r is equal to 0, then what is electric field intensity at the center? It is 0. Because at center small r is equal to 0. Okay. Then what is the electric field intensity on the surface? Electric field intensity on the surface. Electric field intensity on the surface. What is this value? So on the surface, if I will bring this point on the surface, then the small r value will be equal to radius of the sphere, capital R. So on the surface, we can say small r is equal to capital R. So now in this point, in this expression, you put small r is equal to capital R. So here r, here r cube. So 1 r cancel. So you will get Q divided by 4 pi epsilon naught r square. So this is the electric field intensity on the surface, and electric field intensity at the center is 0, and electric field intensity at any point within the sphere is equal to qr by 4 pi epsilon naught r square. Okay. So now you see, so this is the summary, whatever we discussed. So now come to case 2, electric field intensity outside to the sphere. So here you see, so I will take a point, let us say this is B point, which is at r distance from the center. We have to find electric field intensity at the B point. So what is the procedure? We have to take a Gaussian surface. So that Gaussian surface is our Gaussian sphere of radius small r. So here we will find what is the flux through this Gaussian surface. So flux through the Gaussian surface, electric flux through the Gaussian surface, which is passing through which point? B point, is equal to, according to the mathematical expression, it is surface integral of E dot dA over which surface? B surface. And according to the Gauss law, it is total charge enclosed by the epsilon naught. Clear? So that implied, so here E dA cos 0 surface integral is equal to Q enclosure. What is the charge enclosed by this Gaussian sphere? So whatever the total charge is uniformly distributed throughout its volume, that is the total charge given is equal to Q. So those total charge Q will come within this Gaussian sphere. So here charge enclosed by the Gaussian sphere is equal to Q. So Q by epsilon naught. So here E is constant, and area, the integration of total area of this Gaussian sphere is equal to 4 pi r square, because you know for a sphere surface area is equal to 4 pi r square. So that is Q by epsilon naught. So that implied E is equal to Q upon 4 pi epsilon naught r square. So this E is at which point? Outside point. So here we can write the summary. The electric field intensity at outside point is equal to Q by 4 pi epsilon naught r square. But here we see Q is constant, 4 pi epsilon naught constant. So we can conclude that at outside point, electric field intensity is inversely proportional to square of the distance. Okay. So if distance from the surface increases, electric field intensity decreases. And at what point electric field intensity will be 0? So if r tends to infinite, electric field intensity will be 0. And also electric field intensity at the center is also 0, we have already discussed. So this is the summary, and this is all the formula you have to remember. Now see, if we draw the electric field intensity versus the distance, so what will be the nature of the graph? You see, at the center electric field intensity is 0. So this is the center point. So electric field intensity is 0. And at the internal point, electric field intensity is directly proportional to R. So as the point moves away from the center towards the surface, electric field intensity increases in which proportion? Directly proportional to R. That means electric field intensity increases in a straight line. So here within the sphere, electric field intensity is directly proportional to R. So if you come to left side, again from this point to this point, it is internal point. So electric field intensity increases linearly. And what is the maximum electric field intensity? Maximum electric field intensity is equal to on the surface. What is the value of electric field intensity on the surface? Q upon 4 pi epsilon naught r square. So this is the maximum electric field intensity on the surface. Here also you will get maximum. Now, and from beyond r is equal to capital R, that is external point. In the external point, electric field intensity at the outside point, electric field intensity is inversely proportional to square of the distance. So as the distance increases, electric field intensity decreases. So this is the, so here electric field intensity outside point, It is inversely proportional to r square. Here also this is from this r is equal to r. Beyond this you will get external point. So electric field intensity gradually decreases. In which way? It is inversely proportional to r square. So let us discuss example 22.6. So here we have to find electric field intensity of a uniform line charge, that is electric field due to a uniformly charged distributed infinite linear conductor of linear charge density lambda using Gauss law. So what is infinite conductor? You see, you have seen the electrical transmission wire. So that transmission wire is very long distance, very large length. But the area of cross section is very small. So under that condition, it is called infinite conductor. So there is no actually word infinite, so everything is finite. But here length of the conductor is very large comparing to the cross sectional area. If so, then it is called infinite linear conductor. So in this infinite linear conductor, let us say we have given the total charge of Q. So this is infinite conductor. So the total charge given is equal to Q. So Q is equal to total charge given or distributed uniformly over the length of the conductor. Suppose the length of the conductor is say L. So it is infinite. So we are not taking length. Let lambda is called linear charge density. Lambda is called what? Linear charge density. What is the linear charge density? Suppose you take a conductor like this. And the length of the conductor is L. And total charge is equal to Q. So it is uniformly distributed. For L length, total charge is Q. For unit length, the charge is equal to Q by L. So that Q by L is called linear charge density. Okay. So what is the unit? Unit is coulomb per meter. So this is the linear charge density formula. So now we have to find electric field intensity. Suppose I want to find electric field intensity at B point, which is at R perpendicular distance from this linear charge infinite conductor. So what will do? So we will apply the Gauss law. So our aim is to find electric field intensity at B point is how much? Using which law? Using Gauss law. That is our objective. So we know to apply the Gauss law, we have to take an imaginary surface. That imaginary surface is called Gaussian surface. And you will select the Gaussian surface in such a manner that each point on the surface will be symmetric about this linear charge conductor. For that, we have to choose a what? Solid. We have to choose a cylinder surrounding to this conductor. So let us say the length of the cylinder is L. And area, this is the area of cross section. Okay. So now what we'll do? So we have to find flux through this Gaussian surface. So you see there are three surfaces in this Gaussian cylinder. So this is our Gaussian cylinder. The Gaussian surface, which is a cylinder, it is called Gaussian cylinder. On this Gaussian cylinder, we will apply Gauss law. So to find Gauss law, you know we have to find the total electric flux through this Gaussian cylinder. So this total flux is nothing but flux due to first surface. Let us say this surface is equal to first surface. This surface is equal to second surface. And the curved surface is a third surface. Just you see. Suppose this is a cylinder. So this side is one surface. This side is another surface. And this curved part, is third surface. So we are taking curve part is equal to third surface. Clear? So now what we'll do, the total flux is nothing but flux in the first surface, the electric flux in the second surface, and electric flux in the third surface. Third surface is curved surface. So what is flux? Flux is nothing but surface integral of E dot dA for first surface, surface integral of E dot dA for second surface, plus surface integral of E dot dA for which surface? Third surface. So now you see, this is positive charge, this is positive charge. If you take this point, so here electric field intensity is away from it. So this is the direction of electric field intensity. And if you take the small element here, this area vector is always outward. So at a curved surface, you see electric field intensity and area vector both are in same direction. Now take any point, any small element in this first surface. So here area vector always outward. So area vector is always outward. But since this is the positive charge, so electric field intensity at this point is equal to, electric field intensity at this point is equal to away from the positive charge. So this is the electric field intensity. So here angle between electric field and the area vector is equal to 90 degree. For the second surface also, if you take a small element here, area vector is equal to this. This is outward. But since it is positive charge, electric field is away from the positive charge. So this is the electric field intensity. Okay. So now what we'll do? We have to calculate the total flux, electric flux is equal to, in the first surface, you see E and D dot dA. E is equal to in this direction, dA is in this direction. So for the first surface, it will get E dA cos 90. For second surface also, angle between E and area vector is 90. So for second surface, E dot dA is nothing but E dA cos 90. For third surface, so angle between E and area vector is 0 degree. So for third surface, it is E dA cos 0. Now cos 90, 0. So this term will come 0, this term will come 0. So total flux is equal to what? E dA cos 0. You see, if you take every point on the cylinder, the third surface, you see, so let us say in the axial line, in the center, there is axial line. In the axial line, from the axial line to each point on the curved surface, the distance is same. So if distance is same, if distance small r is same from this linear conductor, for every point, for every small element on the third surface, so we can assume E is constant. So E is constant. So dA, what is the integration of dA? Area. So what is the area of a curved surface of the cylinder? Now you see, so what is the circumference? What is the circumference? So circumference is equal to 2 pi r. And what is the length of the cylinder? Length of the cylinder is L. So length of the cylinder is L, circumference is 2 pi r. Then what is the surface area of the core part of the cylinder? You know, it is circumference, that is 2 pi r, into length, that is L. So this is the total surface area. So E into 2 pi r L. But we know, according to the Gauss law, what is the total flux within the Gaussian surface? Total flux is nothing but charge enclosed by the Gaussian cylinder divided by epsilon naught, which is equal to E into 2 pi r into L. Now we will find what is the charge enclosed by this Gaussian cylinder. Now see, within the Gaussian cylinder, what is the length of the charge conductor? That is L. So within this cylinder, this amount of charge, the total charge distributed over this length is our charge enclosed by this Gaussian cylinder. So we know what is the linear charge density, lambda. So charge per unit length, if it is lambda, then within the Gaussian cylinder, this L length of the charge conductor is there. So what is the total charge enclosed by this Gaussian cylinder? So charge per unit length is equal to lambda into L. So lambda into L is the charge within this Gaussian cylinder. That is Q enclosure is equal to lambda into L by epsilon naught, which is equal to E into 2 pi R into L. So this L cancel, we will get E. So what is E? E is equal to lambda by 2 pi epsilon naught R. So this is the expression of the electric field intensity at any point due to a infinite linear charge conductor which is R distance from the conductor. So here lambda is a constant, 2 pi epsilon naught is a constant. So we can say electric field intensity is inversely proportional to distance. So as the distance increases from the linear charge conductor, electric field intensity decreases. So if we draw a graph between electric field intensity versus R, so what will be the nature? So here see, electric field intensity is inversely proportional to R. So as R increases, electric field intensity decreases. So in that way, electric field intensity is inversely proportional to R. So this is the graph. Okay. So now what is the practical aspect? Practical aspect on this problem is that suppose in electrical transmission wire, so we have to maintain the two lines in such a way that the electric field intensity produced by this linear charge conductor should not affect to this conductor. So you have to maintain the gap according to the calculation of this value. Okay, so this is a practical aspect. You see, we will discuss a test here understanding 22.4. In the question it is given, suppose you take an image irregular shaped conductor. So where amount of charge given, let us say this is an irregular shaped, not regular shaped conductor. So you have given total charge Q. Question is, can we apply Gauss law to calculate electric field at an arbitrary position outside the conductor? Suppose I want to find electric field intensity at A point and electric field intensity at B point. So can you apply the Gauss law to find electric field intensity at A and B point? Our answer is definitely no. Why no, you see? Suppose at A point I will take a sphere. Let us say I will take a sphere which is passing through both A and B. But you see the shape of this conductor is irregular. And here if I will apply Gauss law, I have to take an area vector. Let us say the area vector is outward. This is the area vector. But here, due to irregular shape, electric field intensity vector may not lie along D direction. It may lie along this direction. So this is the direction of electric field intensity. And here you see, this B point is very close to this charge body. So here electric field intensity may be more than that of electric field intensity at A. Because electric field intensity depends upon the position of the charge. So here since it is irregular shape, the charge is distributed in a irregular fashion. So the distance from the charge particle to B point and distance of the charge particle to A point may not be same. It is not same. If not same, then the magnitude of electric field intensity at both points are not same. So if not same, you cannot apply Gauss law. Okay. So here let us say angle is equal to 10 degree. Here angle between area vector and electric field is 0 degree. So here angle are different in different position, First point. Second point, electric field intensity magnitude is also different, not same. So in that case, we cannot apply Gauss law. Okay. So what is the condition I have already given? To apply the Gauss law, the Gaussian surface must be symmetric about the charged body, and the angle between electric field intensity and area vector should be always same, whatever may be the surface. And the magnitude of electric field intensity is always constant on the every point of the Gaussian surface. So our answer is no. So with this, today's class I finished. So in the coming class we will try to complete. Definitely we will complete the Gauss law in the next class. So okay, enjoy your day.